Imagine downloading a software update for, an app you've used nearly every single day for years. You get installed, the progress bar fills up, and you open the app to check out the new features.
Right.
But the very first thing it does is deliberately just completely detonate its own database. It wipes out every single piece of historical data you've ever logged.
Yeah.
Just vaporizing years of meticulous records in a fraction of a second, intentionally.
Which is, in the commercial software world, doing something like that would trigger a billion-dollar class action lawsuit.
Oh, absolutely.
It would be a catastrophic failure of engineering. That's the kind of thing that ends careers.
Yeah, but in the world we're stepping into today, that exact mechanism isn't a bug. It's actually a feature. It is a highly calculated, intentional design choice. So welcome to this deep dive. Today, our mission is to peel back the layers of something incredibly rare.
Yeah, we're not looking at some multi-billion-dollar enterprise platform here.
Yeah. Exactly. Not the next viral social media network either. We're looking at a piece of bespoke digital architecture. It's a hyperlocal, completely custom piece of software built by an audience of exactly one for an audience of exactly one. I'm your host, and I'm joined by our resident architecture expert.
Hey, everyone. Yeah, we are dissecting a project called KTrack. And to be incredibly specific for you all listening, we are looking at the source code, the architectural readmes, the domain models, and the deployment pipelines of KTrack version 1.2.3, build 123.
It's very specific.
It is. It's an Android-only workout logging application created by a solo developer who goes by KN, or their Git username is Khashayar.
And if you've ever looked at the architecture diagram for a commercial app, it's usually this very pristine, universally understood blueprint. Everything is built to scale, right?
Yeah.
To handle millions of concurrent users, to sync flawlessly across a dozen cloud servers.
It has to be safe.
Right, it's safe. But when a developer builds something purely for themselves, and they don't have to answer to a product manager or a board of investors or even like a general user base, that standard blueprint just goes completely out the window.
It really does. It becomes an X-ray of the developer's own brain. You start seeing technical choices that are, frankly, wild. They blend these cutting-edge modern frameworks with beautifully brutal old-school data practices.
Yeah.
And the reason we have this massive stack of documentation to go through today is because understanding KTrack is kind of a masterclass in understanding the philosophy of personal software. We really want to figure out the why behind the how.
Let's start with the foundation itself, because the environment this app lives in really dictates every other decision down the line. So KTrack is built exclusively for Android. Looking at the project configuration, it has a minimum SDK requirement of 24, and it specifically targets a framework called Net 9.0 Android. Now, what really caught my eye in the source files wasn't just what was there, but what was aggressively removed. KN went out of their way to explicitly strip out the iOS, Windows, and Mac targets from the project files entirely.
Which is a fascinating psychological indicator right out of the gate. In modern mobile development, the prevailing wisdom is cross-platform.
Oh, there's a cross-platform.
Even if you are only deploying to Android today, you leave the iOS and Windows build targets sitting in the code just in case you ever want to port it. But KN is an Android user. They are basically declaring, I will never need this on an iPhone, so I am not going to let that dormant code clutter my workspace.
It's like refusing to build a bridge to an island you already know you're never going to visit. Why even buy the concrete?
Exactly.
But the actual materials used to build the app are where things get incredibly sophisticated. KTrack is built on .NET 9, but it utilizes a combination of MAUI and Blazor Hybrid.
Yeah, that's a heavy stack.
It is. And I know you listeners are coming from all sorts of technical backgrounds, and that combination of words sounds like deep enterprise jargon. So let's break down the actual mechanics of how those two technologies interact on a physical phone.
Okay, so to understand the mechanics, we have to look at how apps are traditionally built. If you're building a native Android application, you are usually writing in Kotlin or Java.
Right.
And you're using Android's specific UI tools to draw buttons and text on the screen. If you're building a website, you use HTML, CSS, and JavaScript. Now, MAUI, which stands for Multi-Platform App UI, is Microsoft's overarching framework that lets a developer write in C# and .NET, and then MAUI translates that into the native language the phone understands.
So it's basically a translation layer, and the net developer doesn't have to go learn Kotlin. They could just use the C# they already know.
Precisely. But here is where Blazor Hybrid completely flips the script. Blazor is a technology that allows a developer to build interactive, highly dynamic web user interfaces without writing any JavaScript.
No JavaScript at all.
None. They just rate C sharper. So when you create a MAUI Blazor hybrid application, you're doing something incredibly clever. You are building the entire visual interface of the app, the screens, the buttons, the animations, using web technologies, specifically Razor components.
Okay.
But instead of running in Chrome or Safari, those web components are rendered inside a specialized, invisible native web view that MAUI wraps around them.
I love visualizing software architecture, and the best way I can picture this is, the classic ship in a bottle,
Oh, that's a good analogy.
right? The Blazor web code, all the intricate UI logic, the layouts, the colors, there's the meticulously carved wooden model ship. It's built using the tools of a web developer. But a web app can't just install itself on a phone's home screen or access raw file systems natively. It needs an environment.
Yeah, it needs a container.
So MAUI acts as the glass bottle. It perfectly encases the web code, gives it a solid native structure, allows it to be downloaded as a real APK file, and provides a secure bridge for that web code to reach out and actually touch the physical hardware of the Android phone.
That analogy captures the exact mechanism at play perfectly. The glass bottle is what allows this web-based UI to exist in a hostile native mobile environment. And because it has that native MAUI wrapper, the app has direct access to the local file system.
Which is huge.
It is, because it brings us to the core, overriding philosophical directive of KTrack. Absolute local data ownership. There is zero cloud synchronization.
None whatsoever. In an age where even a digital thermometer requires a Wi-Fi connection and an account creation, KTrack just completely severs itself from the internet. All of the data, every single workout logged, lives exclusively on the physical storage of the phone. Specifically, inside a directory path file system.appdata directory ktrack.db.
Think about the apps on your phone right now. They are almost all software as a service. The app on your screen is just a thin client, right? A viewing window.
Just streaming the data, basically.
Exactly. The actual source of truth, your data lives on a server in a massive data center, somewhere in Virginia or Dublin. If you drop your phone in a lake, it doesn't matter. You log in on a new phone, and the cloud populates your screen. By rejecting the cloud, KN is taking on an immense architectural burden.
Because if the cloud isn't managing the state of the data, resolving conflicts, or handling backups, the app itself has to assume absolute, flawless responsibility for data integrity.
Right.
That single SQLite database file sitting on that physical Android phone is the only source of truth in the entire universe.
And that requires building an incredibly resilient local architecture. You are trading the safety net of Amazon Web Services for total digital sovereignty. You own your data, nobody can mine it, and no company can turn off the servers and delete your history.
But the physical risk is astronomical. If you think about the environment where this app is actually used, a gym floor.
Oh yeah, chaos.
You're surrounded by cast iron plates, kettlebells, concrete floors. If a 50-pound dumbbell rolls off a bench and crushes your phone, years of progressive overload data, your entire lifting history is just instantly annihilated.
And that physical vulnerability is exactly why the internal data structure of the app and how it handles backups is so ruthlessly over-engineered. The developer had to create a bulletproof foundation to make that physical risk acceptable.
Let's dive into that foundation. How do you construct a database environment robust enough to handle the chaos of a gym, yet contained entirely on a single mobile device? So KTrack uses SQLite, which makes sense as the gold standard for embedded mobile databases. But the source material shows KN isn't writing raw SQL strings to talk to it. They are utilizing Entity Framework Core 9.
Entity Framework Core, or EF Core, is what's known as an Object Relational Mapper, an ORM. Writing raw SQL queries, typing out select star from workouts where date is greater than X is prone to typos, it's hard to test, and it requires the developer to constantly switch their brain between object-oriented C# and relational database logic.
It's just a context switch that slows you down.
Right. An ORM bridges that gap mechanically.
So instead of writing SQL commands, the developer just writes standard C# classes, and EF Core acts as a real-time translator, converting those C# objects into database rows and columns on the fly.
Yes. And looking at the domain model provided in our sources, KN has designed a remarkably clean hierarchical structure. The entire universe of this application boils down to 3 core entities, 3 C# classes: the workout, the exercise, and the set.
Just 3.
Just 3. The relationships between these 3 dictate the entire flow of the app.
Let's unpack the hierarchy for you all listening. The workout entity is the parent container. It's relatively simple. It primarily exists to track a started.gt timestamp and an end.c timestamp. It defines the temporal boundaries of the session. Inside that container, you have a collection of set entities.
The set is where the actual granular atomic data lives. Every time you lift a weight and put it down, that is a single set entity. It records the weight keg, the reps performed, the duration seconds for things like cardio or planks, and an order integer.
That order integer is super important, right?
It's crucial. It's for tracking the exact chronological sequence of what you did in that specific workout.
And obviously, a set of 100 kilos for 5 reps means nothing unless you know what physical movement you were doing. So every single set must point back to the third entity, the exercise.
Right.
The exercise entity stores a unique string name, like barbell deadlift, and it also holds a Boolean property called ISystem. I found this detail fascinating in the notes. If ISystem is set to true, it means that exercise shipped out of the box with the app's seed data. If it's false, it's a custom movement the user added later themselves.
That iSystem flag isn't just metadata, though. It's actually a structural safeguard. By flagging the 130 or so core movements as system exercises, the app's UI is programmed to completely hide the edit and delete buttons for those specific rows.
So you literally can't delete them.
You cannot delete the concept of a squat from the database, even if you want to. The developer is protecting their own future data integrity by locking down the foundational vocabulary of the app.
Because if the vocabulary breaks, the history breaks. And we see that same protective philosophy in how EF Core manages the relationships between these entities when things actually do get deleted. The database enforces strict rules. For example, if you decide to delete a workout from your history, EF Core triggers what is mechanically called a cascade delete.
A cascade delete is a domino effect written into the database schema. If the parent workout is destroyed, EF Core automatically hunts down every single set that was associated with that workout and permanently deletes them as well.
It just wipes the children.
Exactly. The logic is computationally sound. A set of 10 reps cannot exist in a vacuum without a time and a place. Without the parent workout, the child sets are meaningless orphans, so the database cleans them up automatically to prevent storage bloat.
But the logic flips completely when you look at the exercise entity. If you try to delete an exercise, EF Core imposes a restrict delete constraint.
This is a brilliant contrast. If even one single set in your entire multi-year database history points to the exercise incline dumbbell press, the database will aggressively block you from deleting incline dumbbell press. It throws a hard stop constraint violation.
It makes total sense. If the database allowed you to delete that exercise, suddenly you'd have hundreds of sets in your history that say you lifted 80 kilos for 10 reps, but the pointer to what you lifted would resolve to a null void.
Right, your historical data would be deeply corrupted.
So the database acts as a bouncer, refusing to let you break the internal logic.
And that internal logic is strictly designed to fuel the app's ultimate purpose, tracking biological progress over time. But progress tracking in weightlifting isn't as simple as drawing a line graph of the raw numbers. The data is incredibly noisy.
Oh yeah, training is never linear.
You might lift a heavy weight for a few reps one day and a lighter weight for many reps the next. To make sense of this, KTrack applies a very specific, uncompromising philosophy to what it considers a meaningful data point.
Right, the sources detailed the exact filtering rules here. According to KTrack's internal logic, a set is only considered valid for strength progress calculations if both the reps integer is strictly greater than 0, and the weight K double is strictly greater than 0.
Think about the physical reality that code is mapping to. If you log a set with 50 kilos but 0 reps, the app understands that as an aborted set. Maybe you unrack the bar and realize it was too heavy, so you put it back without completing a repetition.
Yeah, we've all been there.
Exactly. Or if you log 10 reps but 0 kilos, the app assumes it was a bodyweight warm-up, a mobility drill, or just movement prep. In both scenarios, the data represents activity, but not progressive structural load. So the app quietly filters those sets out of your strength charts. It only respects the literal mathematical work done against gravity.
And for pure cardio, it just ignores the weight and reps entirely and looks at the duration seconds property. But for the heavy lifting, how does it normalize that noisy data we talked about? If you do 100 kilos for 5 reps on Tuesday and 105 kilos for 3 reps on Friday, how does the app know which session you are actually stronger in?
It uses a mathematical standard from sports science called the Epley formula to calculate an estimated 1 repetition maximum, or 1 RM. The formula is beautifully elegant. You take the weight lifted and multiply it by the sum of 1 plus the number of reps divided by 30.
Okay, let's run the math on that just to visualize it for you guys. If I lift 100 kilos for 5 reps, I take 5 divided by 30, which is roughly 0.16. I add 1, getting 1.16. I multiplied that by my 100 kilos. So the formula estimates that if I only did a single rep, my absolute maximum capacity that day was 116 kilos.
Exactly. And if you lift 105 kilos for 3 reps, the formula estimates your maximum at 115.5 kilos.
Oh, wow.
So even though the raw weight on the bar was heavier on Friday, the Epley formula reveals that your absolute strength capacity was actually marginally higher on Tuesday.
That's fascinating.
By converting every meaningful set into this standardized estimated 1 RM, KTrack can plot a smooth, single trend line over months and years, cutting through the noise of varying rep schemes.
It's mathematically gorgeous. It takes human sweat and turns it into clean, normalized data. But as clean as the data handling is, this brings us back to that terrifying hook we started the show with.
The nuclear option.
Yes. We need to talk about KTrack's versioning logic, the startup sequence. Because this is where the philosophy of developerware goes to a dark, fascinating extreme.
Yeah, the lifecycle management of this SkySlate database is arguably the most unorthodox aspect of the entire project. In the code, specifically inside mauiprogram.createMaui app, which is the very first thing that runs when the application launches, there is a check against a locally stored device preference called deinitialized for version.
So it checks to see if the version string of the app, let's say 1.2.3, matches the version string saved from the last time the database was opened. If KN pushes an update and the app version increments to 1.2.4, the strings no longer match, and the sequence of commands that fires next is staggering. It calls a method called ensureDeleted, immediately followed by ensureCreated, and then it seeds the database with those 130 default system exercises.
We really cannot overstate what ensureDeleted mechanically does. It doesn't clear a cache, it doesn't trim old logs, it commands the SQLite engine to forcibly drop the entire database file from the physical storage.
Gone.
It completely vaporizes the tables, the rows, the relationships, everything. Then ensureCreated generates a brand new, pristine, entirely empty database shell, which is then populated with the seed data.
It's the absolute nuclear option. If you are a user, your entire workout history, every rep, every weight, every Epley formula calculation over years is gone the moment you launch the updated app. Why on earth would anyone architect software to intentionally self-destruct its own state?
Because writing database schema migrations is one of the most miserable, tedious tasks in software engineering.
Explain schema migrations for someone who hasn't had to suffer through writing them. I know they're a headache, but why?
Let's say you have a commercial app with 10,000 users, and you want to add a new default exercise to your seed data, or you want to add a new column to the sets table to track rest times. You cannot just drop the database because your users will lose their data and riot.
Naturally.
Instead, you have to write a highly complex migration script. The script has to read the old database structure, gently alter the tables without locking the app, carefully insert the new seed data without duplicating existing records, handle any conflicts if the user happened to create a custom exercise with the exact same name as your new system exercise,
Oh, man.
and verify that the data integrity holds up across thousands of different phone models.
It's like trying to rebuild an airplane's engine while it's flying at 30,000 feet.
It takes hours of development, testing, and debugging. But remember, KTrack has an audience of one. KM looked at that monumental engineering headache and realized they could just bypass it entirely by exploiting their own local backup system.
So what does the workflow of a version update actually look like for the developer? Walk me through the physical steps.
The source material implies a very strict manual ritual. Before KN installs the new APK they just compiled, they open the old version of the app. They go into the settings, they trigger a manual database backup, saving their years of history to a secure folder on their Android device.
Okay, so the data is safe in a separate file.
Right. Then they install the update, they launch the app, knowing full well the app is going to detect the version change and nuke the active database. The app vaporizes everything, recreates the fresh schema, and injects the new updated list of 130 system exercises.
And then KN is sitting there with a totally empty app.
Yes. And at that point, they go back into the settings, invoke the restore function, pick the backup file they just made, and manually inject their historical workout data back into the newly seeded database.
That is just, it's a breathtaking trade-off. It's like moving out of your house, hiring a demolition crew to bulldoze it to the ground, having builders construct an identical house with slightly updated plumbing on the exact same lot, and then carrying all your furniture back inside. And you do this every single time you want to upgrade the plumbing.
It sounds absurd when you describe it physically, but computationally, for a solo developer, the math is incredibly sound. Writing those gentle schema migration scripts might take 4 hours of frustrating coding and testing. The manual backup nuke restore ritual takes maybe 45 seconds on the phone.
Yeah, that's a huge time save.
By accepting the nuclear update process, the developer reclaims their time. They build a brutal tool for themselves because they're the only one who has to live with the brutality.
But that brutality is strictly confined to the back-end administration. Because when we step out of the architecture and onto the actual gym floor, the user experience of KTrack tells a completely different story. The app is hyper-optimized to get out of the user's way.
The juxtaposition between the harsh database lifecycle and the smooth user interface is striking. And the speed of that user interface is achieved by making what enterprise developers would consider a severe architectural compromise. Let's look at the Razor pages, the actual UI files that render the screens. In KTrack, there is no repository layer.
I know from reading devlogs that the repository pattern is practically a religion in enterprise software. What exactly does it do, and what is KTrack doing instead?
In a massive corporate application, you never let the user interface talk directly to the database. You build an abstraction layer in between called a repository. If the UI screen wants to display a workout, it sends a request to the repository. The repository translates that request, talks to Entity Framework, gets the data, translates back, and hands it to the UI.
A lot of handoffs.
It keeps everything strictly separated, which is great for a team of 50 developers who need to write independent unit tests without accidentally overwriting each other's database entries.
It's like having a chain of command. The frontline worker isn't allowed to talk directly to the CEO. They have to pass memos through middle management.
Precisely. But middle management introduces latency and requires a massive amount of boilerplate code. In KTrack, the Razor pages inject an interface called IDB Context Factory directly into the UI logic.
Meaning the frontline worker is kicking open the CEO's door and shouting commands. The user interface is directly wired into the SQLite database engine.
It is considered a cardinal sin in enterprise architecture because it tightly couples the presentation layer to the data layer. If the database schema changes, the UI code instantly breaks. But KTrack isn't an enterprise app. By throwing out the repository layer, KN eliminates hundreds of lines of useless middle management code. When they click Save Set on the UI, that command fires straight into the skillet file with zero abstraction overhead. It is raw, unadulterated speed.
And you need that speed because the environment the app operates in is deeply chaotic.
Let's talk about the physical reality of using a smartphone in a gym. You are not sitting at a quiet desk. You are sweating, breathing hard, wearing chalk. And more importantly, you are constantly multitasking on the device itself. You switch apps to change a Spotify playlist, you open a browser to check the form on a new exercise, you answer a text message.
And this multitasking exposes a critical vulnerability in the Android operating system, which is memory management. Android is notorious for aggressively terminating background applications to free up RAM. If you are 45 minutes into a grueling leg day workout, you switch over to Spotify for 2 minutes, and the OS decides KTrack is using too much memory in the background. Android will quietly murder the app.
And if the app hasn't permanently saved those 45 minutes of sets into the squat database yet, that data is just gone forever. That is incredibly frustrating. It's the kind of thing that makes you want to throw the phone against the wall, which is exactly why KTrack implements an extraordinarily robust, deeply pragmatic draft system. We see this implemented in the workout new.razor file. The app doesn't wait for you to hit a final save workout button to protect your data.
How does it protect it in real time without constantly hammering the SQLite database and slowing the app down?
It bypasses the database entirely for the active session. Every single time you interact with the workout screen, every keystroke, every rep you add, every exercise you select, the app instantly serializes the current state of the entire UI and dumps it into a lightweight raw text file called workoutdraft.json located in the app data directory.
So it's just rapidly writing a cheap JSON file in the background.
Exactly. Writing to a text file is incredibly fast and takes almost zero computational resources. Now imagine Android's memory manager kills the app. The next time KN opens KTrack, the startup logic checks that app data directory. It sees the workoutdraft.json file sitting there. Before the UI even fully loads, the app reads that file and instantly rehydrates the screen to the exact millisecond state it was in before the crash.
The workout survives the operating system's executioner. That is brilliant. It's a localized life raft. And the source materials show several other design choices specifically aimed at reducing friction on the gym floor. There's a feature on the UI which, by the way, has a very distinct aesthetic. utilizing a deep purple top bar, hex code 2BROB5A, and an orange floating action button. But there's a specific button labeled Copy Last.
The psychology behind the copy last feature is my favorite part of the gym floor UX. When you are performing multiple sets of an exercise, logging the data becomes deeply repetitive. You don't want to manually type 100, then tap the next box, then type 8 for 4 sets in a row. It takes you out of the physical zone.
It introduces mental friction. The Copy Last button functions exactly like autofill in a web browser. With a single tap, the app queries the database for the very last set you logged for that specific exercise, pulls the weight and the reps, and pre-fills the input boxes. You hit one button, the data is instantly populated, and if you happen to do one extra rep on this set, you just tweak the number. It shifts the cognitive load from data entry to data verification.
They apply that same ruthless friction reduction to the exercise selection menu. When you want to add a new exercise to the workout, a search box appears with a live autocomplete dropdown. But KN programmed a very specific behavioral quirk into it. The exact millisecond the user's typing creates an exact match with an exercise in the database, the search box instantly hides itself.
It doesn't wait for you to hit enter. It gets out of your way the second its job is computationally finished. It anticipates the completion of the task.
It is the epitome of flow state design. And we see that same desire for speed and efficiency in how the app visualizes progress. When you navigate to the exercise progress.razor page to see your history, you expect to see a chart. In modern web and hybrid app development, if you want a chart, you almost always import a massive third-party JavaScript library like chart.js or Syncfusion.
Right, because writing the logic to draw axes, plot points, and handle scaling is a nightmare. You just hand your data to the library and let it render the visual. Why didn't KN do that?
Because those libraries are incredibly heavy, they add megabytes of bloat to the application size, and executing complex JavaScript inside the MAUI web view takes time. It introduces latency. The screen might take half a second to render. KN refused to accept that latency. Instead, KTrack uses raw SVG line charts.
Scalable vector graphics. It's drawing the charts using raw mathematical geometry.
Yes. The Razor component takes the historical data, the session dates, the top weight, the calculated EPLI 1RM, and it dynamically generates raw SVG markup. It literally writes the coordinates for an SVG polyline inside a viewbox dimension of 320 by 80 pixels.
That is hardcore.
But the result is spectacular. Because it's just native vector math and basic markup, the browser engine inside the MAUI wrapper can draw those trend lines in less than a millisecond. It requires no external dependencies, no heavy JavaScript execution. The chart appears instantaneously. It's a perfect example of trading developer convenience, importing a library for absolute runtime performance.
Okay, so the gym floor experience is frictionless, blazing fast, and aggressively protects your active data. But we have to tackle the elephant in the room. Data is only useful if you can access it, share it, and ultimately rescue it from the nuclear version updates we discussed earlier. Let's look at the mechanisms for exporting the iron.
Exporting takes two forms in KTrack: sharing a specific workout and backing up the entire systemic database. Let's start with sharing, which is handled on the workout.detail.razor page. It utilizes an MAUI API called share.default.requestAsync.
For you listeners, that's the API that triggers the native Android share sheet. When you want to text a funny photo to a friend or send a link to an email, that little menu that slides up from the bottom of your phone with all your contacts, that's the share sheet. But KTrack isn't sharing a photo or a URL.
No, it is dynamically compiling a raw text file. When you hit share, the app loops through the data of that specific workout. It writes the workout name and the date at the top. Then it groups everything by the exercise name, outputting a highly readable string format. Something like barbell bench press, 100 kilograms, 8 reps, 0 secs. It writes this .txt file to the app's secure cache directory and passes that physical file to the Android share sheet to be texted or emailed.
And there's a brilliant, nuanced detail in the source notes regarding a recent bug fix for this feature. The branch was literally named Bug Workout Share Should Not Be Sorted. They actively had to go into the code and remove a sorting algorithm from the share output. Why would you want unsorted data?
Because a workout is not a spreadsheet. It is a chronological narrative. Think about the physical reality of a training session. You might start with light squats to warm up, then you move to heavy deadlifts, then you finish your session with high-rep, light squat variations to burn out the muscle.
The sequence tells the story of the physical fatigue.
Exactly. If the sharing algorithm automatically sorted the text file alphabetically by exercise name, it would group the warm-up squats and the burnout squats right next to each other, destroying the timeline of the session. By explicitly removing the sorting logic, the output file relies on that set.order integer we discussed in the domain model. The .txt file accurately reflects the reality of the physical session exactly as it occurred in time.
It's a great example of domain-driven design. The code bends to the reality of the gem, not the other way around. Now, sharing a text file is relatively straightforward, but performing a complete database back up the lifeline that saves KN from the ensure deleted update cycle that requires diving into the absolute bedrock mechanics of Squelette.
The backup and restore mechanisms live in settings.razor, and backing up a live active database is fundamentally different from just copying a normal file like a photo or a PDF. You can't just tell the OS, copy KTrack.db to my downloads folder.
Why not? If it's just a file sitting in the app data directory, why can't I just duplicate it?
Because of a deeply complex performance feature inside Squelette called write-ahead logging, or WAL. When you interact with KTrack, let's say you log a heavy set of bicep curls. Squelette doesn't immediately open the main ktrack.db file, find the right row, write the data, and close the file. Opening and modifying massive files takes time, and doing it constantly would make the app feel sluggish.
So what does it do instead?
It writes that new transaction to a separate temporary sidecar file called a WAL file, usually named ktrack.db-wal. Think of the WAL file as a waiting room. It is extremely fast to just quickly toss new data into the waiting room.
Okay, so my set of bicep curls is sitting in the WAL file. It's safe, the app knows it's there, but it hasn't been merged in the main database file yet.
Precisely. Now, imagine you try to manually copy the main ktrack.db file right at that moment to make a backup. You are copying a file that is technically out of date. The recent bicep curls are still stuck in the waiting room sidecar file. If you restored from that copied main file later, you would be missing data. Your backup is structurally corrupt from the perspective of recent time.
So how does KTrack solve this? How do you ensure the main file has everything before you copy it?
The app has to forcefully intervene in the database lifecycle. When you trigger a backup, the code executes a command called a WAL checkpoint.
It forces the database's hand.
It acts as a strict bouncer. The checkpoint commands SQLite to halt all new transactions, take everything currently sitting in the WAL file waiting room, and permanently flush it into the main ktrack.db file. It merges the reality. Once that checkpoint is fully completed, the code knows the main file is 100% up to date. Only then does it read the bytes of that file and use the file saver, default API, to let KN save the perfectly synchronized backup somewhere safe on their Android file system.
That is a fascinating peek under the hood. But the restore process, when KN survives the nuclear version update and needs to inject that backup back into the fresh app, the mechanics of the restore process feel so manual they're almost violent.
The restore process exposes the raw, unapologetic machinery of the underlying frameworks. It starts smoothly enough the app uses a native file picker UI to let the user navigate their phone and select the .db backup file they previously saved. But what happens next is an intense sequence of manual system overrides. First, the code calls a method named clearAllPools.
I know from tinkering with database code that connection pooling is a huge deal. What is a pool, and why does the app need to clear them?
Entity Framework Core is designed to be highly efficient. Establishing a new connection to a database takes computational time. So EF Core keeps a pool of active connections open to the Squelette file, holding on to them just in case the UI needs to ask for more data quickly. Because those connections are open, the Android operating system places a strict lock on the physical ktrack.db file. The OS says, this file is currently in use by a process. It cannot be deleted or overwritten.
So if you try to paste the backup file over the active file, Android will throw an access denied error.
Exactly. clearAllPools is a manual override. It forces Entity Framework to aggressively sever all of its active connections, dropping the connection pool to 0, and thereby releasing the operating system's lock on the physical file.
The door is unlocked, but the sources show it doesn't just copy the file over immediately. It does something else first. It manually deletes the LakeWall and shim sidecar files.
We talked about the WAL file being the waiting room. The SUM file is a shared memory index that Squelette uses to keep track of the WAL file. If you are about to drop a completely different database file from last week into this directory, leaving the old sidecar files sitting there is incredibly dangerous. The Squelette engine might wake up, look at the old WAL file, try to apply those transactions to the newly restored database, and irreversibly corrupt the entire structure with ghost data.
So the code methodically assassinates the sidecar files to ensure absolute sterility in the directory. Then, and only then, does it copy the user's backup file over the active DB path.
And there is one final crucial step before the app forces a reload to the home screen. It runs a schema migration.
Wait, hold on. We literally just spent an entire segment talking about how KN utilizes the nuclear interdeleted update specifically so they don't have to write schema migrations. Why are migrations suddenly running during the restore?
They avoid writing complex data handling migrations for the seed data, but EF Core itself still needs to verify the structural shape of the tables. Imagine KN restores a backup from version 1.1, but the new app is version 1.2, and version 1.2 expects the sets table to have a brand new column called order. The old backup file obviously doesn't have that column. EF Core detects this structural mismatch and automatically executes a lightweight structural migration, silently injecting the missing order column into the restored SQLite file so the new C# objects don't crash when they try to read it.
It makes sure the old data physically fits into the new blueprint. When you lay it all out like this, the architecture has a profound split personality. On the gym floor, the app is a masterpiece of commercial-grade UX. It has automated drafts, autocomplete search, gorgeous SVG charts, and one-tap autofill. It hides all the friction. But the moment you enter the administrative settings to handle your data, the velvet rope drops, and you are manually flushing wall checkpoints, severing connection pools, assassinating shared memory files, and orchestrating database schema migrations.
That split personality is the defining characteristic of true developerware. When the developer is acting as the user, tired, sweating, lifting weights, they want zero friction. They want magic. But when the developer is acting as the administrator, they want the raw, brutal machinery exposed. They do not want the framework to hide the complexity. They want absolute granular control over the life cycle of their data bytes.
And what's truly mind-bending is that this desire for absolute control isn't just confined to the code inside the app. It extends all the way out into the cloud, governing exactly how the app is built, compiled, and physically delivered to the phone. This brings us to the final, and perhaps most paradoxical piece of the KTrack architecture, the CI/CD pipeline.
We have spent the last hour establishing that this is a localized, offline, cloud-hating application built for an audience of one. And yet the source code reveals that KN has wired this project into a massive, enterprise-grade, continuous integration and continuous deployment engine Azure pipelines.
For you listeners who aren't deeply entrenched in DevOps, setting up an Azure pipeline is not a trivial weekend task. In massive tech corporations, entire departments are dedicated to managing these pipelines. When a team of 50 software engineers writes code, they push it to a central server. The pipeline is an automated robot that takes all that code, compiles it in a pristine virtual environment, runs thousands of automated tests, and packages it into a final release binary. KN has engineered this massive corporate infrastructure for a solo gym app.
Let's trace the execution path of this pipeline because the level of automation is staggering. According to the Azure DevOps configuration files in the repository, the pipeline is set to trigger automatically the moment KN pushes new code to the master branch on Git.
So KN writes a new feature on their laptop at a coffee shop, types git push, and the cloud robot wakes up.
Exactly. The first thing the pipeline does is spin up a pristine virtual machine agent in a Microsoft data center. It specifically requests an image running Windows latest. Once the virtual machine is booted, it doesn't just grab the newest tools available, it enforces strict architectural discipline. It reads a file in the code repository called global.json.
And the sources note that global.json explicitly pins the .NET SDK version to exactly 9.0.305, not .NET 9, not the latest version, exactly 9.0.305. Why mandate that level of microversion precision?
Absolute reproducibility. The worst nightmare in software development is the phrase, "It works on my machine." If the pipeline just pulled the latest available version of .NET, Microsoft might have pushed a minor update the night before that introduces a tiny undocumented change to how MAUI compiles Android resources. The app would fail to build on the server, even though it builds perfectly on KN's laptop. By cryptographically pinning the exact SDK version in global.json, KN guarantees that the build server is a perfect, immutable clone of their local development environment.
So the pipeline installs the exact required version of .NET. What happens next?
It runs a command called .NET Workload Restore, specifically installing the MAUI Android workload into the virtual machine. The server is now capable of compiling mobile apps. It builds the code. But an Android app isn't ready to install just because it's compiled. It requires cryptographic security.
Right. Android devices will refuse to install an application unless it is digitally signed with a cryptographic key, proving the identity of the developer who built it.
And managing those keys is traditionally a massive headache, but KN automated it. The pipeline reaches into Azure's secure file storage and downloads a highly encrypted file called KTrack-release.keystore. It also pulls down hidden pipeline variables, the key store password, the key alias, and the key password. These are secrets that are never committed to the public Git repository. The pipeline seamlessly passes these secrets into the compilation command, cryptographically signing the final binaries.
And what are the actual artifacts that pop out at the end of this massive automated assembly line?
The pipeline is configured to produce two distinct release-ready artifacts. First, it generates a signed APK file. An APK is the traditional Android application package. This is perfect for direct sideloading. KN can download this file directly from the Azure portal and install it on their phone via a USB cable or a private download link.
Bypassing the Google Play Store entirely.
Exactly. But remarkably, the pipeline also produces a signed AAB file, an Android app bundle.
The AAB is the strict, modern format explicitly required by the Google Play Store to publish an app globally.
Yes. So even though KTrack is an intensely personal piece of developerware, complete with a self-destructing nuclear database update that would infuriate public users, the deployment infrastructure is fully weaponized and ready to deliver the app to a global storefront at a moment's notice, should the developer ever choose to pull that trigger.
Okay, I'm going to play the skeptic here. You've laid out this incredible architecture. We are talking about a solo developer logging their kettlebell swings into a local ski slide file. They have set up a cloud-based Microsoft Azure Enterprise pipeline. They are spinning up Windows virtual machines, managing secure cryptographic cloud storage, passing hidden environment variables, and cryptographically pinning microversions of the .NET SDK. Isn't this the ultimate definition of over-engineering? Isn't this just absurd overkill for a personal side project?
If you analyze it purely from a perspective of initial time investment, yes, it probably took KN hours to perfectly calibrate that pipeline. But if you analyze it from the perspective of developer psychology and the preservation of flow state, it is one of the most brilliant investments they could make.
Explain how that preserves flow state.
Think about the friction of manual deployment. Imagine KN writes a cool new feature on a Sunday afternoon, maybe adding a new chart to the UI. If they didn't have this pipeline, they would have to open a command prompt. They would have to type out the complex compilation command. They would have to manually type their cryptographic key store password. They would have to wait 5 minutes for their laptop to lock up while it compiles. They would have to navigate through deep folder structures to find the hidden APK file, upload it to Google Drive, and then download it on their phone.
That sounds like system administration, not creative programming.
It is deeply tedious, and it breaks the creative momentum. By automating every single piece of that deployment process, KN has removed the friction of iteration. Now, they write a cool feature, type git push, close their laptop, and go make a cup of coffee. By the time they pick up their phone, a perfectly compiled, cryptographically signed, installable application is magically waiting for them. When you eliminate the administrative chore of deployment, you are exponentially more likely to continue improving and iterating on the project. The massive enterprise automation exists solely to protect the joy of personal creation.
It creates an invisible bridge directly from the developer's imagination to the physical device in their pocket. So as we bring all of these pieces together, we have been on an incredible journey through the source code of KTrack. It's a masterpiece of architectural contradictions. We're looking at an app that violently rejects the cloud, demanding absolute localized privacy. Yet, it leverages the most powerful modern hybrid web technologies like Blazor and MAUI to exist. It features a gym floor user experience that is incredibly forgiving, anticipating user friction with auto-fill drafts and blistering fast SVG charts. But it pairs that UX with a raw, brutal, unforgiving SQLite database lifecycle that literally nukes its own history to avoid writing update scripts. And this entire fiercely independent ecosystem is backed by the heavy-duty enterprise-grade deployment machinery of Azure DevOps.
It is the ultimate synthesis of what software looks like when a developer only has to answer to themselves. Every single choice, no matter how paradoxical or frightening it might seem to a traditional corporate architect, serves a deeply specific, highly personal purpose. It is perfectly optimized for the exact physical and psychological needs of its creator.
And seeing software built this way leaves us with a profound concept to mull over. We are so used to the commercial model of technology. We expect apps to be universal, accessible, constantly syncing to the cloud, constantly tracking our analytics, and built to appeal to millions of generic users. But what happens when we possess the skills to build software that is so intimately tailored to our own brains? When an app anticipates our specific friction points, catalogs our physical history in our own custom formats, and lives entirely on hardware we physically control, does it stop being just a tool? Do these hyper-personal applications become something closer to a second memory? By turning away from the commercial cloud and building tools purely for ourselves, we might be abandoning the shared universal language of modern UI design. But in an age where every commercial application is desperately trying to mine our data, sell us a monthly subscription, or trap us in an ecosystem, perhaps building a bespoke ship in a glass bottle is the only true way to reclaim our digital autonomy.
It is the purest expression of digital sovereignty.
It really is. At the start of this deep dive, we talked about how commercial software is like a clean, universally understood blueprint of an office building. But KTrack is that messy, beautiful, hyper-specific X-ray. It might not make sense to anyone else's anatomy, but for the one person it belongs to, it is the only picture that matters. Keep diving deep, keep questioning the digital architecture around you, and we'll see you next time.